Okay, let's go ahead and get started today. Some of you observed that I kind of was on a grading marathon today. So both projects 1 and 2 are graded. If you have any questions about how your grade was determined, of course, please talk to me. I mentioned this explicitly in a few cases, but I want to mention it in general. If it didn't work out quite the way you wanted, please work on a revision. Go ahead and clean it up and so forth. So for the most part, projects 1 and 2 went quite well for most of the class. So if it didn't quite go well for you, don't give up hope. May just be a rocky start. I'm happy to work with you to help you understand what's going on and get things into slightly better shape. Okay. And then project 3 was due today. The RAM was due. Yes.
Can you please explain the PC?
The PC?
Yes.
Okay.
Yeah.
So, what is the PC? PC is a special register called the program counter. Conceptually, what's going on with the program counter? Let me quickly glance at the book just so I can see a reference to the specification for the circuit. This will just take a second. So that one, it's not actually talked about a whole lot in the book, but let me give you an idea of what's going on with it. So this is a register. It contains a 16-bit value. And I don't remember exactly what the HDL said, but I'm pretty sure it was something like the following. It's clocked, of course. Has an input, and then something saying whether or not, so then there are sort of 2 choices. Do we replace the input, or does it just go up by 1? So I think there was like a 1-bit input signifying that. Does that sound familiar?
There was increment.
What's that?
There was increment and reset.
It was called increment?
Yeah.
Okay.
Also load and reset and reset.
Okay, good, thank you. So there would be increment, then a load, and a reset, something like that. One way you could think about this conceptually is something like a stopwatch. You tell a stopwatch to start, it goes up by 1 every time for a while. You can pause it, you can reset it. This is a lot like that, although the metaphor is a little strained, actually, I'll have to admit. So, what are the functions of this chip? Well, first, let me talk about its ultimate purpose, and then let's walk back and look at the functions. Its ultimate purpose is going to be to figure out where it is in a program. So, what's that going to mean? So I'm actually going to bleed into today's prepared lecture a little bit, and then we'll bleed backwards into this. As you all know, we're going to have 16 kilobytes of RAM in our computer. And these are going to be addresses represented using 14 bits. And I'm sure you are all painfully aware of how to deal with those 14 bits at this point. So this RAM, this read-only memory, is being used for the purpose of allowing storage of data during the execution of a program. It's where data structures are going to go of various kinds. It's actually not where programs are going to go. Get a feel for that. Want to talk a little bit about the most amazing consumer device of my childhood. what amazing consumer device might this be? It was called the Atari 2600. I don't know. Have you ever heard of this wondrous device? Oh, wow. Wow. I mean, wow. Okay. What the computer we're building in this class is going to be a close cousin to the Atari 2600. For those of you not familiar with it, let me describe roughly how it works. So it was like a small computer, and it had like this little thingy coming up here, and then there was a little slot, and in that slot you would place a cartridge, and there would be wires coming out of it that would go to your TV, and then you'd have joysticks coming out of it. Now, this is an absolutely amazing machine. To really give you a feel for what was amazing about this machine, this thing had about 4 kilobytes of RAM. Okay, that was it. And these cartridges were about 4 to 16 kilobytes of ROM, read-only memory. So the idea was you would plug in a cartridge like, say, Pac-Man. I don't know if any of you ever saw Atari 2600 Pac-Man.
We used to play it when we were kids.
Sweet.
Yeah.
Nice, nice. It is not the definitive rendition of the game. Pac-Man was pretty blocky. Instead of dots, there were dashes, and it made sort of a charming bop, 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 bop noise as it ate. But they achieved all this in with 4 kilobytes of RAM for the data structures, 4 to 16 kilobytes of ROM for the program itself. So as you can imagine, to reason about how a program works in this kind of a domain, you have to be careful in terms of how you split up the address space. So I'm just guessing here, but my guess is that the memory layout for the 2600 had the 4 kilobytes of RAM in the first 9 bits of the address. That's not right. 12 bits. Then, basically, if the 13th bit was a 1, you then had your cartridge memory here. Okay? This cartridge memory consisted of a computer program. There's one instruction of the computer program in each address in memory. Now, here's the thing. If you want to run this program, you need to know where you are, right? It's kind of an issue. So that's where the program counter comes in. So the program counter keeps track of which instruction is the next instruction for the CPU to execute. So let's think about what this means for the kinds of updates we're going to be making to this register. First of all, we need to have a way of setting it to a value. Why is that? Our first instruction isn't going to be at memory location 0. It's going to be at memory location 4096. How did I know that? I've done this stuff a lot. The last memory location in the 4 kilobytes of RAM is 4095. 4096, that's 2 to the 12th power. So that's going to be the starting location for any program loaded on that cartridge. That is to say, the system is wired such that when you plug in the cartridge, the memory address starts at 4096. Okay. So you read the instruction, you execute it. By you, I mean the CPU and the computer. So the CPU finds the instruction at 4096, executes it, and in the normal way of things, where do you think it's going to get the next instruction?
4097.
It's going to come from 4097, right? And then the next one will be at 4098 and so forth. Except every once in a while, it stops just sort of marching in a line, and it jumps around somewhere. Now, why is it going to have to do that? Well, conceptually speaking, if your program is doing something like an if or a while, it needs to move around to another spot, you know? like just think about the way we lay out an if statement in a language like Python. You've got if some condition, blam, else blam sub 2, right? And so if the condition is false, you need to jump straight down to blam sub 2. If the condition is true, you do the first block, but then you need to skip the whole else, right? And so those are called jumps. And so with a jump, what we do is we tell our program counter, you're not actually going up by 1. Instead, you're going to go where I tell you. Just because I told you. I'm the CPU, I'm the boss. I can do that, right? So our program counter really needs to be doing quite a lot. By default, what it's going to do on each step is go up by 1. But sometimes it's just going to get replaced completely by some other value because we have to skip around in memory. So coming back here, how does all this fit in together? This INC, if that's a 1, then, oh, of course, we have an out. Pardon me, forgot about that, right? So if this INC is a 1, then whatever it was, so basically you're going to have out at time plus 1 equals out of the previous time step plus 1. That is, you take what you've got and you increment it by 1. If you do a reset, I think that just sets it to 0. I don't remember for sure, though. I haven't glanced at that particular one in a little while. If load is a 1, then it's going to replace it with whatever you're getting from in. Whatever you're getting from in is going to be the new value of the program counter. So next week, when you build your CPU, you're going to be really glad you have this. You're going to be using it a lot. Does that help answer the question? Yeah. Cool. Good question. Other questions so far? All right. So let's think about this whole idea of machine language. So what we're going to do this week is we're going to write machine language programs. The purpose of this is to help you all have an idea of what the CPU is supposed to be doing before you actually wire it up as a circuit. So this week we're going to write programs that run directly on a CPU. Next week we're going to create the CPU itself. So a machine language instruction is a bunch of zeros and ones. On our machine, instructions are 16 bits. They are 16 bits. This particular machine language, it's very complete in the sense that it's sufficient for expressing any algorithm as computer scientists normally conceptualize them. But boy, can it not do very much by itself. And to be fair, all machine languages are like this. Every instruction does a very limited amount of computation. In particular, they're all really going to come down to something like this. So kinds of instructions. This is very informal, loosely speaking. What are the kinds of instructions? Move a value. And moves can be from memory to the CPU, or they might be from the CPU to memory. So a lot of what a CPU does is it basically says, memory, fetch me this value so that I can do something with it. Now, for a CPU to be able to do that, it needs to have its own storage on the chip. So what this requires is that the CPU has its own registers. So the CPU registers, these are just registers like you developed for Project 3. There's nothing special about them aside from their location, which means everything. By being on the CPU, they're in kind of a special category by their very presence therein. So every CPU has registers. The Commodore 64 and the Atari 2600 had a closely related CPU. So both of those had about 5 or 6 registers. A typical modern CPU will have up to 64 registers. The one we're developing is going to have like 3. Keeping it simple, but it's enough. It's enough. Okay? So moving a value, that's a big thing a CPU does. The other big thing it does is math. And so typically, one or both operands are in registers. Okay. Oh, and of course, there is the idea of a jump. So reset the program counter in some appropriate way. And really, in any machine language, all the instructions are basically one of these 3 things. Move a value, do some math, or jump. That's really all they do. Okay. So our CPU has 2 main registers. The third register is the program counter. 2 main registers are called A and D. A and D. Okay, so what do they mean? How does this relate to the 16 bits? So bit 15 in an instruction says an awful lot about what it's going to do. Okay? If bit 15 is a 0, then what happens is bits 0 to 14 are immediately stored in the A register. So if bit 15 is a 0, bits 0 to 14 go into the A register. So the idea here is you want to set a value in the register on the CPU. That's the kind of instruction that you use. Okay. So other instructions, bits 15 to 13 are actually going to be 3 ones. So all the meaning of the instruction comes from the other bits. Okay. And so for your reference, pages 66 to 67 in the book are going to help a lot here. So something like this is clearly in the move a value territory. Instructions of all 3 types we will see in bits 15 to 13 are all 1s. The way that this CPU is set up, you can actually combine them sometimes. So you can do some math and then immediately ship the value out to memory, that kind of a thing. Different CPUs have different philosophies there. Some CPUs will strictly do all the math in the processor registers and have memory moves be a separate sort of thing. Others like to mix things up. Ours is slightly more in the latter category. So the next 7 bits, so this would be bits 12 through 5, I think. 12 through 6, sorry. Bits 12 to 6 are going to specify a computation. So this specification is given on page 67. So bits 12 to 6, there's a chart there, and you can basically read off the chart and see what it's going to do. Now, you might find that this chart looks kind of familiar. You might find it looks kind of familiar. it might in some ways remind you of the ALU. Just maybe. No guarantees. Okay. But it may remind you of the ALU just a little bit. So the way you can think about the specification of a computation, generally speaking, is that this is what's being sent to the ALU. So we have the ALU, and you remember it's got these X and Y inputs, okay? You can think about it is kind of like D is your X and A is your Y. And then the way that D and A get combined depends on what you've told the ALU to do. Now, there's another trick, which is bit 12 is called the A flag. Bit 12 is pretty sneaky. What it lets you do is if A is equal to 0, it means the computation is being done with the A register. If A equals 1, then the contents of the A register are interpreted as a memory address. And so when A equals 1, it actually goes to main memory and looks up a value. Okay, so that's the computations it does. Now bits 5 to 3, these are called the destination bits. Okay, so these bits specify where a computation winds up, and these are given on page 68. And so really, these can wind up in any of these three places. They can go to the A register, the D register, or the memory location indexed by the value in the A register. Any of those places are possibilities. Okay. And then finally, bits 2 to 0, these are jump conditions. Okay, so what happens with these is that if that condition is true, then we jump to whatever address is given by the A register. So you look over all of this, and you might be thinking, yeah, if it comes down to it, I can write the zeros and ones. I can sit down and I can work out the zeros and ones I need to use. But I'd hate it. I would hate it with an almost unspeakable passion. I could do it, but I'd hate it. Funny story, I was at an exhibit at the Science Museum in West Palm Beach, Florida, where I grew up, with my dad. And they were having an exhibit on old computers, actually. And so they had there this computer that had 8 switches that could go up or down and then just one button. The idea being you could program it in machine language by flipping the switches to be zeros and ones and then entering the instruction. Yeah. And so I made a crack to my father about, wow, what an ancient machine. I can't imagine programming on that thing, et cetera, et cetera. Well, my father finished college in 1969, and his first job was with International Business Machines, IBM. And so his rejoinder was, well, I programmed on something like that in my first job. Whoa, but we don't have to do that. Now, why is it we don't have to do that? What miracle brings this about? That miracle is called an assembler. Okay. An assembler is a program that takes a program written in what's called assembly language, then spits out machine language. the idea of assembly language is to set up some kind of means of encoding these machine language instructions such that they're comprehensible, that they're somewhat more human readable. Okay? So that's what an assembler does. You're actually going to create an assembler in Project 6, which is going to be a lot of fun. Assemblers are pretty cool to write. The key thing to keep in mind about assembly language versus machine language is that there is a one-to-one correspondence between the assembly instructions and the machine language instructions. So for every machine language instruction, there's a corresponding high-level assembly language instruction that you can actually use instead. So what we're going to do this week, actually, so project 4, which I'm assigning today, it will be due next Tuesday, starting to slow down the pace a little bit. We do Tuesday, is we're going to write 2 programs in assembly language. Then we have available in our tool suite a CPU emulator. We're going to run the CPU emulator, load our assembly language programs into it, and then it's going to simulate their execution on our computer. So yeah, it's going to be a lot of fun. So let me go over what an assembly language instruction is going to look like for us. Okay? They're pretty low level. They're going to look pretty cryptic, but for the most part, they're going to be a lot nicer than writing down 16 ones and zeros. So what are some of our assembly language programs going to look like? Well, you remember I mentioned there were 2 different modes of instruction depending on bit 15. Right? Okay. Well, in assembly language, you can use the @ sign and then some memory address. So I'm just going to throw a number here. Okay? And that is the assembly language for the stuff this value into the A register. So in general, @V means place V in the A register. Okay. Now what about all these computations? Okay, the way we're going to set up computations, so now we're getting into, so this bit 15 is a 0. Now we're getting into bit 15 is a 1. Whenever bit 15 is a 1, it means that we're doing some kind of computation. Okay? And the syntax here is going to be a little off, but I think it'll make sense once you get in the right mindset. So, among other things, what you can do is set a destination and a computation. So what might something like this look like? You might have something like d equals d plus 1. So what does this mean? It means this is our destination. So the destination bits for the instruction are going to be set accordingly to whatever's on the left-hand side of the equal sign. This is our computation. So the 7 bits giving us the computation are going to be determined based on that. So how do you know what you can use? Make sure you have a bookmark and you slide it over on page 67. Looking at that a lot. Okay? So there are all kinds of computations that you can perform there on page 67. All kinds of computations you can do. So this is just an example. So as long as you're not doing a jump, the basic syntax for an instruction is you have a destination is equal to a computation. A destination is equal to a computation. Okay, so what about jumps? Jumps are sort of funny, okay? As I mentioned, most jumps are conditional. So there is a unilateral, I must jump, but for the most part, they're conditional. How does the condition determine? Jumps, they depend on the ALU output. So a typical jump instruction might look something like the following. And so these are given on page 69. Again, a well-positioned bookmark will be very, very helpful. Okay, you may even just photocopy those pages and have them out or something. So here's a typical jump instruction. D semicolon JEQ. Now what does this mean? The D, that's a computation. That's a computation. Note the lack of an equal sign. If there's no equal sign, the ALU still does a computation. The ALU always has to be told to do something. Okay? But it's not going to store the value anywhere. Instead, it's going to do a jump. Now, how is it going to know what jump to do? JEQ means jump if the value is 0, if it's equal to 0. What are some other J's? Well, there is JMP, which is jump no matter what. If you're going to do a JMP, you don't really care about the ALU, and so a typical syntax is something like 0 semicolon JMP. 0 out the ALU, just go. What are some others? JGE, jump if greater than or equal to 0. JNE, jump if less than or equal to 0. Or no, that was JLE. I'm sorry. JLE, jump if less than or equal to 0. JGT, jump if greater than 0. JLT, jump if less than 0. So you have greater than or equal to versus greater than versus less than or equal to versus less than. So those are all possibilities. And then JNE is jump if not equal to 0. So anything but a 0 is okay. Mention these are all on page 69. But those are the 6 jump options that you have. Now, putting all this together, you can actually achieve quite a lot. To give you all a feel for this, I can talk about this stuff all afternoon, but I think actually writing some assembly language programs will give you a better idea of what you're going to be undertaking. So let's do that. I got a little annoyed with WordPad, and so I'm going to try out Notepad++, which I've heard is a pretty good Windows text editor. So let me play with the font here, as in I just installed this right before class. View. I'm trying to figure out how to blow up the font. Settings, yeah. Preferences. Editing. Really, you got to give me a font here somewhere.
Maybe after you're writing, you can make that one too.
Let's see. Document. Language menu. Tab settings. Line numbers. Maybe MISC. Can't believe it doesn't have a font. Oh, zoom in. Okay. Neat. All right. So let's write a program that adds 2 plus 2 in assembly language. Okay. So let's see what this is going to look like. So what? Why can't? Oh, that's the keyboard that doesn't work. That's right. There we go. That's cool. All right, nice big font. So what you're going to find is writing assembly language programs are going to be frequently alternating between at something and then another kind of instruction. So you typically set the A register and then do something else. So at 2, okay? Now I also, I want the number 2, I'm going to add 2 plus 2. So my strategy is going to be to have a 2 in the D and a 2 in the A. So I'm going to say D equals A. And now D equals D plus A. So at this point, I have added 2 plus 2. And so this is a first assembly language program. So let me save this. Let's throw it on my desktop. Well, there's got to be a no extension here somewhere. All types, there we go. Sweet. So I'm going to call this 2 plus 2.asm. So asm is the usual suffix for these things. All right, now I'm going to start up my CPU emulator. So, it's hiding here somewhere. There we go. So I'm going to go to CPU emulator. Okay, so I'm going to load a program. I'll go to my desktop. I'm going to load 2 plus 2. And so notice that it says ROM and RAM up here in the CPU emulator. ROM, that's going to be where your program is. RAM, that's going to be data that it updates in some way. So down here, we have a map of what the CPU is doing, okay? So the value in the data register is here, and then the ALU operations are here. The program counter is over here, and the A register is over here. So the idea is that we can watch step by step what our assembly language programs are doing. And just warming up with this single stepping is essential, just to understand what this code does. So first I have my at 2. Now notice my A is now a 2, and my program counter is now a 1 because that's the address of the next instruction that I'm going to fetch. Okay, so now I'm going to continue a single step. D equals A. So now we have A is 2 and D is 2. When I said D equaled A, that meant my ALU output became a 2. So my A just kind of passed through my ALU. And now I'm going to say D equals D plus A. So I single step again. Now notice my ALU computation is D plus A. So whatever computation you specified for the ALU on the preceding instruction is going to be shown to you inside this beautiful green trapezoid. From here, you can see the 2 inputs coming into the ALU. You've got your D and then either your memory or your A. And now the ALU output is a 4, and so is the D. So this short program demonstrates how we might add 2 plus 2. Any questions up to here? Any questions? Yes, Nick.
So I created a notepad file and set it to save as all files, but it wouldn't load because it wasn't a hack or ASM file.
You have to save it as a .asm, and it should work. Yeah, that's what I just did. Yes, Faisal.
Why do we need the line D equals A?
So I wanted to add 2 plus 2. The only way to put a specific value in a register is to load it into A with the at.
Right.
I don't have an A plus A ability in my ALU. So see, if I look at page 67, it lists all the possibilities. There's D plus 1, A plus 1, D plus A, D minus A, all this good stuff, but there's no A plus A. So if I want to add 2 plus 2, I have to copy that value into the D register, and now I've got 2 different things I can add. Yes, is it Mason?
Yes.
Okay.
You couldn't just say D equals 2.
Correct, because that is not, 2 is not a value that the ALU can produce by itself. Now, I could say D equals 1, D equals -1, and D equals 0. And the reason I can say those things is those are ALU outputs. Actually, you all probably remember engineering those as ALU outputs. Right? So I can set those up no problem. But since the ALU can't just natively output a 2, I actually have to stuff that in the A register, and then I can copy it over to the D register. Yeah, Jolly.
So if we had done that, you have kind of bypassed the 8, like D equals 1 and D equals.
Right, I could go D equals 1, D equals D plus 1, and now my D equals 2. But then I still need to add 2 plus 2, my A still needs the 2. And so then I might say something like A equals D or whatever. Yeah. Yeah.
Can you make the last line to be A equals D plus A when you do execute the operation in the A register?
Oh, definitely. Yeah, yeah. So A and D and a memory location are all legitimate destinations. And so, yeah, I can do that. I can totally do that. All right. Other questions so far? Okay. In order to do anything involving storage beyond the CPU, we need to play with memory. I mean, that's just essential. You got to store stuff in memory. I mean, I've got my 4 sitting in my D register, but the point of CPU registers are to be a very temporary holding location for data. I mentioned that many modern CPUs have lots of registers, like 32 registers, 64 registers. So often what a really high-tech snazzy compiler is going to do is actually stash local variables in registers to save the memory access. So that's a really common thing for a smart compiler to set up. For us, that's not going to be an option because we just don't have that many registers. So let's say we wanted to put this somewhere in memory. So let me come back here. Whoop, not quite there, but here. Okay. So now let me say I wanted to put this in memory somewhere. There we go. Oh, no. There we go. Okay. So what I now need to do is set my A register to the target memory location where I'm going to store the value. So let's say I am being grossly uncreative, and so I decide, I'm just going to stuff this at location 0 in memory. I'm going to set my A register to 0, and now I will say M equals D. So let me go ahead and save this. Let me load it into here. So now I have my 5-line program loaded. Let's step through it and see what it does. I put a 2 into my A. I set D equals D plus A. Now I've got a 4 in my D register. This next instruction, I set my A register to 0. And now I'm going to say M equals D. Notice RAM location 0 now contains a 4. RAM location 0 now contains a 4. So I have taken a value and I have moved it into memory. I have stored it in memory. So coming back to my source code, now let's say I want to just add 1, say. What I could do, so let's see. Yeah, so let's say I'm just going to add another value to it. I could say something like the following. So let's say I want to add 3. Oops. So these 2 instructions set the contents of my D register. Now I want to mess with memory location 0. Say M equals M plus D. Actually, it needs to be D plus M. Let's save this. Let's load and run it. So D has a 2, D equals D plus A, D now has a 4, 0, M equals D, M has a 4. Now I put a 3 in my A register, D equals A. I zero out my A register, and now I'm going to say M equals D plus M. So watch memory location 0 very carefully. It's now a 7. 4 plus 3 equals 7. Yes?
Why does it matter if it's D plus M instead of N plus D?
The assembler is not guaranteed to recognize M plus D. The syntax of the assembler is such that if it sees D plus M, that tells it the bit pattern to use for the instruction, and by implication, the ALU. If I put M plus D, it's not in one of my columns, and so it might not assemble, actually. So I'm just saving myself some heartache. Right, and that's a great point. These are just mnemonics. These are not full-blown algebraic expressions of any kind. These are just simple textual mnemonics for the underlying machine language instructions. If you want algebraic expressions, you need a high-level language. How long, you might be wondering, did it take people to get to that point? The first electronic digital computer came online around 1945. The first compiler for a high-level language, that language was Fortran, came online in 1955. So people actually ran out of patience with this stuff within 10 years of the invention of the first working computer. Wow. Yeah. So there it is. So I want you all to take note of everything we've done so far. We have loaded specific values into registers. We have performed additions. We have done memory stores, and here we have done memory lookups. Believe it or not, this is almost everything you need. The only thing we haven't done so far is a jump. Right? So let's write a program with a jump. So let's come back here. Let's set up a new file. So how about for this program, we'll add 1 to some memory location some number of times. Sound good? Sure. So it's going to be like we're doing a kind of like a for loop, but not so elegantly, like by a lot. All right, so let's say we're going to for loop, I don't know, 5 times. I want to go 5 times. Now I need a memory location to track how many more loops I have to make. So to keep this simple, what I'm actually going to do is make this a countdown. I'm going to make this a countdown, okay? So what I want to do is get this value into D, and now I'm going to use memory location 0 as my counter. like so. So these 4 lines are roughly equal to, you know, x equals 5 in Python. This is a phenomenon that pervades all assembly languages. Something you could have done in 1 line in a high-level language can take 3, 4, 5, 10, or 20 lines in assembly language. Because the instructions are just really, really simple. Okay, so I've set up my loop counter. Okay. How about this? We'll double the value every time, and we'll start the value at 1. So let's have our value be at memory location 1. Okay. Now, because the value 1 can be a direct output of the ALU, this variable was a lot easier to set up. I didn't have to go through D. I could just say, I want you to be a 1. And there we are. Okay. So now we're ready to start. So here's the thing, right? It can be an inordinate irritant to calculate the destination of a jump. So a really amazing thing that an assembler does for us is provide what are called labels. So in other words, we can just pick a string to be the name for some line of code, and then we can use that when we talk about our jump destinations. So how do you set up a label? What you do is use parentheses and then give it a name. I'm going to call this label here, just because. Okay. So now my first step is to double the contents of my memory location. So how am I going to do that? Well, I'm going to put a 1 in the address register, and then I'm going to say D equals M. So I'm copying the value from that memory location into my D register. Then I'm going to say M equals D plus M. So see, I've taken that value, copied it into the D register, and now I'm adding it back to itself and storing it back in memory. Having done this, I now need to know, decrement my counter, right? So my loop counter is at memory location 0. Because I'm just decrementing it by 1, I can say M equals M minus 1. Now, here I can do a jump. If this is not equal to 0, no, actually I can't quite do a jump. Okay. M equals M minus 1. Actually, we can even do this. We can store a value in both M and D at the same time. Okay? I'm just checking the table to make sure I have it in the right order. Yeah, MD. And so page 68 has those mnemonics. So I want it in both M and D. Why is that? I want my memory location updated, but once I set the address for the jump, I want the value to be in the D register to prepare me to jump. So I'm going to go at here. And now I'll do a read from the data register and jump if not equal to 0. So what I have now done is I have created a loop by jumping back to that earlier memory location. Now, if we were doing this in machine language, we not only would have the inestimable pleasure of doing all of these numbers in binary, we would also have the inestimable pleasure of every time we edit the program to insert or remove a line, we would have to recalculate the jump address over here. I think you would all agree with me. Forgive me if I'm speaking for you out of turn, but I think you would all agree with me that that would be an unutterable pain in the rear. Recalculate every time and convert it to binary. So assemblers are great things. And something that's really great about an assembler is that because it's a one-to-one correspondence of the instructions, the assembler doesn't cost you anything in performance. Yeah, this is sort of a basic axiom of assembly language programming. See, if you want the absolute maximum efficiency for a program, the best way to get it is to write it in assembly language. In practice, we don't really want it that badly, which is why we use high-level languages. High-level languages with really good compilers can generate amazingly good assembly language programs that might rival what a human could create, but not always. Like, generally speaking, at the current technology, any sufficiently skilled assembly language programmer can defeat the best compiler. But a really good compiler is going to be defeating the majority of assembly language programmers. I know people that are working on trying to address that situation. But for now, that's where it is. So in any event, there we are. So let's try this out. Save this as loop. And let's make it an all types. Oh, loop.asm. I'm going to load loop.asm into my emulator. Notice this RAM is still a 7, so I'm going to hit the reset button. Oh, and it's still not a 7. All right, you can edit it directly if you want. So I just did, because I can. All right. So let's walk through this. All right, I now have my 5 at location 0. I now have my 1 at location 1. And now I'm entering my loop. So m equals d plus m. So my 1 has now doubled to a 2. Now I'm going to update my memory location and the D register. So note that md equals m minus 1. I've got a 4 here and a 4 there. Now, the jump target is location 6. That got computed for me by the assembler. Okay? And so it loads D and does a jump if it's not equal to 0. And sure enough, it's not, and so it jumped back. It jumped back. And so it's really just going to do everything again. M equals D plus M. So it's now a 4. Now I decrement my counter. I've got a 3 in both memory and the D register. And now I'm going to check my D. Jumps up again. And so it goes. I'm up to an 8 now. I'm up to an 8. My counter is down to a 2. And it jumps. Up to a 16. My counter is down to a 1, and it jumps. I'm up to a 32. My counter is down to a 0. And it goes on to the next line. The program counter is updated. And so this is a program with a loop, which I think is pretty cool. Any questions up to here? Yeah.
Would there be a more efficient way to make this loop? Or is that,
What's that?
Would there be a more efficient way to make that, or is that kind of just bare bones?
That's bare bones. Bam, make it do it. Yeah, it doesn't get much more efficient. I mean, there is no overhead here.
Right.
Yeah, there is no wasted code here. This is as tight a loop as it gets on this CPU. Other CPUs might have other things they can do, but this loop is tight. Good. Other questions so far? Yeah, Nick.
How would we end the program?
Well, that's sort of a funny question. So, it doesn't really end, right? It's sort of a funny thing about assembly language programs. You run them, and they just keep running. They don't really stop. If it stopped, it would be like, what's the computer supposed to do now? So, in practice, if you're assigned a program like multiply two numbers, just so that I can hit the fast forward, you know, what I would want you to do is have a last line that just jumps around to itself. So what would that look like? So it'd be something like the following. No matter what, oh, it'd be like end at end 0 semicolon JMP. Yeah, and so this just loops endlessly. It just loops endlessly. So I can save this. In fact, can load it in here. And now, let's say I just want to run through it really fast, like. And so now you see it sort of histrionically bouncing between the last two lines. So that'll do nicely, because that way I can run it fast, or you can run it fast while you're testing it, and then see, oh, did it give me the right data? Did it give me the right results in memory? Yeah. Now in practice, what happens, right, is every computer has some kind of constant loop requesting input, right? Sort of at the deepest, most bare bones level. You know, so you imagine something like Windows, you know, your operating system has deep down some program which like throws Windows up or whatever, right? And then waits for input from those windows. The most more primitive machines tend to have something like a command line, you know, just waiting for you to type something and eternally waiting for you to type. In fact, one thing we haven't really talked about so far, but is crucially important, is how are we going to do I/O in assembly language? I mean, we've done programs that do stuff to memory and read stuff from memory. We haven't really done any I/O. Life's pretty dull without I/O, right? So the main way to do I/O in an assembly language program is what is called memory mapped I/O. So let me go over this conceptually with you all. So let's think about output first. Okay. The overall strategy here is that we wire some part of our address space to the display hardware. Okay, so the way that that works on our machine is something like the following. We have a black and white screen, okay? And this screen is 512 by 256 pixels. It's black and white. So a pixel is either on or off. So how is this going to work? Well, starting at memory address 16384, note that the final address in our 16K RAM chip is actually 16383. So the next 8K are screen memory. So to build the computer, you would wire your display device such that when you store a value at these addresses, the signal goes directly to the device. It's memory mapped I/O. You map memory locations to the I/O devices. So how's this going to work in practice? Well, each of these memory locations contains 16 bits and correspondingly represents 16 distinct pixels. So what's this going to look like as a program? Let's find out. So let's say we just want to draw a couple of dots on the screen. Okay? So let's pick some memory location. I'm going to go with 20,000 because I know it's somewhere kind of in the middle of the screen. Okay? Then I'm going to say m equals -1. Now, why -1? Thoughts? Why did I pick -1?
To tell it to turn the pixel off.
On, actually.
On.
Right. So I want to make this location be all ones. So that should give me a nice dash, 16 bits across. Okay? And guess what? That's the whole program. Dang. All right. Let's call this -1.asm. And I'm going to make this all types. And let me load up -1. Here we are. All right. So I'm going to run this program. Check out my dash. There it is. There it is. You know, so I could change that address to move the dash to all kinds of different locations on the screen. And that's how I get output. So these same basic tools of assembly language that we've already been looking at, doing computations, reading values from memory, storing values in memory, are the exact same tools we use for I/O, actually. And this is just how it works. You know, this is the way any typical computer is going to operate. Deep down, all that a graphics library is doing is shoving bits into memory locations that are directly wired to a display device. Of course, they're really wired to the port, and then the port has the right number of connections and all that stuff. But you get the idea. You get the idea. Okay. Oh, 5 minutes. We got time for input also. So we'll take a first glance at input, and of course, we're going to go over all of this in much more detail next time. So what about input? The only input we have is the keyboard. Okay? Now, the way this is set up is at memory location 24576, we have a key press. Okay? And this is going to be a lot of fun to play with. So let's write another program to be our first keyboard program. Okay? So we're going to do a loop so that we can be constantly watching what it's doing. Okay? So I'm going to have a label for the start of the program. And then I'm just going to say at 24576 D equals M, and then 0, then at start 0 semicolon JMP. So it's going to jump all the time. All right, so let me save this program. I'm going to call this key 1. .asm. All right, so let's load this up. And I'm actually going to go to View Animate, and I'm going to turn off the animation. Then I'm going to run it, and I'm going to start typing keys. So the keys are appearing down here. And darn it, it is not doing anything cool with my deregister. We're going to do a better version of this program next time where we'll display something graphical to correspond to the characters. Okay. But you can see this is the input device, and the values are certainly there. But I turned animation off to get nice keyboard response, and now we can't see the stuff. So I'm going to play with this a little more. I'll show you Thursday. Let me briefly go over what the assignment is. Okay? You're assigned to write 2 programs in assembly language. One of them is going to multiply 2 numbers. This is mult.asm. And so it's going to look at values in memory location 0 and 1, and it needs to multiply them. And there's some test scripts to test it out. The other program you're going to write is going to be called fill.asm. The way this is going to work is whenever any key is pressed, it's going to start blackening the entire screen. When you lift a key, it's going to start turning the screen white again. And that's what it'll do. So you'll be playing with both input and output on that one. So I think I've given you a nice overview here. For next time, I encourage you to probably start the multiplication program. I've shown you everything you need to do that one. We're going to look a little more at I/O next time. If you start between now and next time, you can also come ready with questions about how you do stuff in assembly language. So have fun with it. I'll see you on Thursday.